Michael just said that I'm going to give the talk, but in fact I'm going to introduce the students who did all the work and will do all the talk. That's just the way it goes, you know. You may have remembered me saying these things 2 years ago, a year ago, you know. Here are the students who did all the work. So, second degree of separation. These are former students. Well, Ryan and, well, Javier we met later, but so it goes. Who now have their own company with the beautiful logo that evokes the river and the green hills of New Hampshire. So we're going to talk about 8215.4. This was an effort that we started a while ago. What came out of that was the packet and packet that we did with Travis Goodspeed. Unfortunately, Travis could not be here, but in fact he's with us in spirit. In your attendee bags, you should see the International Journal of Proof of Concept, or GTFO, and you will find there an article of his that gives a further bypass of various WIDSs and WIPSs in 8215.4. So, International Journal of PFC or GTFO, ladies and gentlemen. So, Zigbee, right? Why is it there? Why are we looking at it? It was supposed to be the simpler Wi-Fi, and it was supposed to take over the world. It was supposed to be in building automation, you know, smart energy, green energy, smart buildings, green buildings. It was supposed to be in healthcare, which is scary, wireless health, sudden death, that sort of thing. It was supposed to be, and now is coming to your homes, talking to your thermostat, talking to that thing in your basement that burns fuel and gives you heat. Emphasis on burns fuel. And a whole lot of other things. Certainly industrial automation, factory floor where you don't want people tripping over cables, but you want to talk to all of those devices that are basically whirring away and opening up valves and pipes in which your toxic chemicals flow, and things like toxic chemicals. So all of those things, right? What do we call them? We call them the attack surface. So you're introducing dependency on all of those on a wireless protocol that is supposedly simpler than Wi-Fi, but well, we'll see how it works, right? And there is the rights principle that Joshua Wright came up with when he presented Killer Bee, the tool for Zigbee manipulation that started it all. And the principle sounds: security will not get better until tools for practical exploration of the attack surface are made available. Joshua Wright, work on Killer Bee duties. So unless you can poke at each and every layer and prepare conveniently and inject conveniently the payloads at every layer, you are not going to have an improvement in security. And this is what this device that we'll be releasing today. This is what this device does, among other things. It's your frame injector on the PHY layer. So let's go through this protocol layer by layer. This is what a frame looks like. So these are ones and zeros, nibbles of them, nibblefuls of them, flying through the air. And this being radio, it needs to synchronize. So you have the preamble, during which the radio gets adjusted to your clock, to the transmitter's clock. Then you have a magic number, A7, that starts the frame. And then you have the length of the frame, and you have the body. And then that body constitutes what you see on the link layer in your Wireshark. Now, these are jitterings of the ether. These are bytes in the air. These are bits in the air. There are no frames. Frames are already an abstraction. The phi layer lies to you. I mean, if you look at the saying that it received a frame, that there was a frame, there was no such thing. There was actually a bunch of jitterings of the air, of the electromagnetic field in the air, and the chip has a tiny machine that matches every nibble it receives, every byte it receives, against the magic value of the sync. And then it thinks it goes into the frame mode. This is very significant. When, at some point in the past, my wife asked me, well, you keep talking about packets and injecting packets and crafting packets, but what are packets? How do you know that you're actually in a packet? And I mumbled something about encodings and preambles, and I did not understand it back then. That, in fact, the frame was a lie. There was no frame. There are only very simple machines that make that illusion. And layers of abstraction become boundaries of competence, which I did not transcend at the time. So what you have with Zigbee is a radio chip that knows how to pull nibbles, bits, out of the air and match them against this magic value, which, by the way, can occur in the body of the message as well, in exactly the same shape as it gets transmitted over the air. So observe that curve carefully. That chip, usually it's not actually just a chip. You can sort of see the chip, but there is the guts of the radio around it, antenna and all the little capacitors and resistors that I don't understand all that well. So these are the hardest thing to get, and they took the longest time on those, on those modes, and I don't know how to do them. And then there's a microcontroller. A microcontroller talks to this radio over some very simple bus, like the serial bus, and essentially reads and writes registers on that radio chip. One of those registers is the magic value of the sync and the length of the preamble. Beyond that, it's your most familiar step in which you already have the concept of a frame. So, and then the packet and then the payload. And this is it. So this is the lie that we tell to children. So the first lie that we tell to children is that there is a link layer, right? And of course the link layer contains things like the frame control, the bits that determine what this frame is, and the sequence number, and who it is for, and who it is from, and here, and eventually the control sum. So this is where it becomes hairy.
Thank you. So what I'm going to do now is go through exactly how hairy it is, right? So if this is sort of the overview of the entire frame, then you'd start breaking out where optional headers are. And now one Affimote free giveaway for whoever can tell me first 2 fields on this which are related. So one has a dependency on another. There's plenty, I promise. So does that question make sense? Two parts of the specification that are dependent. So you can't use this one, an address field, which is dependent on the frame control field's addressing mode, right? That would be a relation. What? Good enough. And abort. So really, there's quite a few. And the relations between those are a pain. And this is not even the entire specification because I ran out of space on the slide. One of the things that we previously presented is Scapy layers to help you deal with this mess. And so, as Sergey mentioned, there's the phi layer at the bottom, right? And these are the lies that we tell. The 2 in red, the phi and the Mac layer, are called 802.15.4. So when we talk about that in the presentation, that's the IEEE spec, which covers these. From here on up is the Zigbee layer, and that is That's another specification, not an IEEE spec, but an industry working group which defines that. And so there's different topologies, mesh or star networks. There's different device classes from fully powered, full functionality devices to reduced functionality devices like a door or window sensor. A shout out to some of the people, obviously Josh, who started this work, Travis, who worked on the PIP paper and really led that with us. We previously released the Killer Bee framework, building off of Josh's work, some Scapey, the fingerprinting work done under Sergey at Dartmouth, which you'll see some of the results here for the first time in the end of our talk, and other neighbors. So Sergey got at this earlier, right? To be able to interact with these, this isn't Wi-Fi or Ethernet where you have in each of your laptops an interface to be able to speak this protocol. So what we want to do is we've looked over a ton of existing hardware that we've used for about 3 years that we've been really involved with playing around with these at the low layer. The Atmel RZ USB stick is nice, but it needs an in-circuit programmer, and it has an internal antenna. The SDRs are expensive, and you have to do GNU radio, but they're very nice at getting into the PHY layer. And perhaps the one that we landed on and liked the most of these was the Telos B, which was developed for playing with sensor network design. And it has an external antenna, and you can program it over USB, but try to get one in the United States at least, and you will be
disappointed.
Yeah, angry, I was going to say. But you guys may have more luck over here, given I pay about 65 euros for shipping every time I need one, on top of the cost of the board. So what are we presenting today, right? We got tired of all of that. And I mainly got tired of it, and then one of the electrical engineers who works with me, Javier, does the circuits and actually makes it work. So what did I ask for, right? An external antenna, a CC2420 radio, which is an extremely, it's a little older, but it's extremely low-level control over your radio registers. The ability to program over USB, because I'm lazy when I do my firmware development. Onboard storage, so we can take it away from the computer, add some headers to it, battery power it, and have some fun when we throw it over a fence, right? And so that's what it would look like. And here's actually what it would look like. And they tell me I can put it here, and you can see a real one if I do that. Oh yeah, well that's not. Maybe my paper is more fun. But anyways, we will have them around afterwards, and we can all play with them. So now that we've shown, and you'll have to take my word on it, that you can sniff with this, Javier is going to guide us through how can we do some defense.
So now that we solved the first challenge and we can sniff packets, we want to be able to do cool stuff like detect attacks. So we have to do 4 general things that include capturing the packets, storing the packets, analyzing the packets, and then generating some kind of alert. So right now, if you wanted to do that, you have to manage each interface manually, and it's a pain. So we came up with a framework to do that. So we developed Beekeeper WIDS, and the idea is right now it's a simple proof of concept framework developed in Python that does those 4 things for us. So it's got 4 major components. The first one is the interface, like the app remote. Now that's going to interface with the wireless spectrum and grab your packets. It's going to forward them to a drone. The drone interacts with the WIDS system that we see here. So it'll task the drone and say, hey, I want these packets on this channel. The drone will manage the interface, grab those packets, forward them to the WIDS, and then the WIDS will run some analytics on it. And then we have external applications like the CLI that we'll see later in the slides that let us interact via our REST interface. So this is sort of a detailed look of the drone. Its main responsibilities are to manage the interfaces. So if you have a single interface, you can sniff on a single channel at any given point. If you have multiple interfaces, you can either sniff on multiple channels, or you can sniff and inject, sniff and jam. You can do a bunch of different cool stuff. So each drone is composed of the daemon, which has a simple web server that exposes the services via REST API, and it has the plugin. What's cool about the plugin is that it uses the hardware functionality to provide a basic capability, like capturing packets, injecting, jamming, and we've designed it in such a way that users can write their own plugins to extend the functionality of the drone. So if you want something very specific, some very specific front-end filtering, you can implement it in your own plugin. So let's take a quick peek at how, can we have the lights turned off so that we can see this a little bit better? So here I hope you guys can see it. For the sake of time, we're just going to show a demo. Here we start by turning on the log viewer. Here we start initializing the drone with Zigbee drone tech run. We can see the log saying it's starting. Here we're starting in this corner a fake listener that's going to mimic the WIDS. So when it captures packets, it'll forward them. And we've got something just to demonstrate that we're actually receiving them. Meanwhile, in the background, we actually have a traffic generator continuously running. So now that it's up, it enumerated the interface, it found it. We're running Zigbee drone with the task command. So the goal here is to send an instruction to the drone to say, I want you to run the plugin capture on channel 15 with some UUID we made up. And here we're specifying callback. Here's where I want you to upload your packets. And this is conveniently the fake listener we stood up just to demonstrate. And to the capture plugin, we're passing the parameter filter, and we're just saying, give me anything that you find. So you can see it uploaded, and all of a sudden we start receiving packets. Now, if this were not a demo example, instead of this fake listener we put up, it would actually be forwarding the packets to the WIDS system, and it would store it in the database. Cool. Can we have the, actually I think the lights are on for now. The lights are fine. So before we move on to how we actually detect the attacks, we want to do a quick overview of what some of the attacks are. So here we have a number of different categories like sniffing, injection, tampering, jamming, collision, exhaustion. There's all sorts of different attacks that we can try to detect. And for each different type of attack, we may need different detection techniques. So today we're going to focus on 3 specific ones that all work by capturing packets. And that may or may not have something to do that's the only plugin we've written so far. So let's take a look at the first one we're going to look at, which is AES-CTR. So AES-CTR is a specific Zigbee security mode that tries to provide both encryption and replay protection. So it provides the replay protection by looking at the frame counter and saving that value, and then subsequent frames cannot have that same frame. So if you see frame counter 5, and then you see it again, it's potentially a replay, so the radio just discards it. And that's the way that it was implemented, so it was a flawed design. So as the attacker, if you send a spoofed frame with a frame counter of the maximum value, FFFF, and even with garbage data, you don't have to have the right encryption key. The radio will receive it, it will decrypt it, it won't know that it's a garbage packet, but it'll still look at the frame counter, update it, and then any subsequent packet that it gets, because it can't be higher than FFFF, you've maxed it out, it'll discard the packet. So you can very easily, with a single frame, DOS that network. So in the next slide, you'll see that using the Killer Bee framework, it's extremely easy to implement this attack. In the first box, we're creating the packet. In this middle box, we see the FFFF, we're setting it to the max value, and then we're injecting it. So it's very simple to do in just a couple lines of code. So now that we know the attacks that we're looking for, we can talk a little bit more about how the analytics portion of the framework works. So we saw how we can task a drone, and we saw how the data gets uploaded. So the WIDS daemon is responsible for exposing its services as an API, receiving the packets, and storing them in the database. And then that lets modules query the database to see those packets and then run some analytics. And then it will generate some alerts if it finds them. So we want to show another quick demo. So if we can lower the lights again, please. So here are the commands that we're going to run. We already saw Zigbee drone tech run. We're also going to start the WIDS, and we're going to start monitor alerts to see them. So here we're doing, for debugging purposes, we're opening the log viewer. Here we're starting the WIDS system. and the monitor alerts. So all of these, the logs and the monitor alerts, they're calling the REST API to get this data. So it's very easy for a third application to interact with the WIDS system. So now we're going to add the drone. So the drone from the previous example is still sitting around running. We're going to tell the WIDS system that's just kind of empty, we want you to use this drone to perform your stuff. Then we're going to manually load the module. In this case, is DOS AESCTR detect. And when we launch that module, we're going to see it up in the log view. A bunch of stuff starts to happen. Here in the module settings, we're going to specify the required settings, which for this module is the channel 15. So in the background, not shown in this slide, we're running an attack script that will actually generate this traffic. So it'll generate the traffic, the drone will see it, it will sniff it, because we told it, the module told it to look for a very specific, only for specific frames with this security mode enabled. And then hopefully shortly we will see the drone starting to upload the data, and it's down there, here. It received the packet. So when it does that, it'll save it into the database, and then the module that we loaded will be able to query and search for it. So any second here, we should see flurry of activity. I think this particular module refreshes every 60 seconds.
Yeah.
So there's the data being uploaded, like we pointed out. And during the next refresh cycle, the module will query the database, will find the packets, and then here we go. It issued, it detected the alert. I think that's the end of the demo. If we can have the lights back on.
If I may jump very quickly in. So what you're seeing is a very simple attack. And so you should be asking yourself, why are we seeing it? Why does the stack fall over on such a small thing? And the answer is the same as why did the early TCP IP stacks fall over when somebody sent an overlong ping packet? The answer is, well, there were no convenient tools to send an overlong ping packet. So the people who were building such systems, who were building those stacks, did not have the opportunity to run 1,000 tests instead of 5. So what you're seeing is supposed to make the world a safer place by making it easier for people, for the actual engineers, to break their systems and to test their systems. And what we're doing is the equivalent of raw sockets. Here, send this buffer over into the medium. Let the medium jiggle so that all the other receivers receive it. And the better your control, the more granular your control of the medium, this is given to us by a chipcom chip that is talking and giving and receiving those jitters. And we can do this on the level of the radio nibble, radio symbol, that is a unit of transmission. And that is what this is all about. This is your raw injection capability, a fast reactive jamming capability, if you would like that, at the wire speed, at the wireless speed rather. Yeah, at the smallest granularity there is.
It's really tough to do reactive jamming on wireless. A lot of fun.
And now you can do that with AP mode. And by the way, so you may have detected a certain B in the bonnet kind of scheme. So, you know, Zigbee, killer bee, AP mode, AP culture is the art of the keeping of bees, apis in Latin is a bee. I don't think that was a very smart choice of a name. Yeah. Facepalm.
So that's exactly right. And one of the things that we wanted to accomplish with this framework is to start it off sort of as a research tool, with the killer bee framework to launch attacks, and with this to see how we can potentially detect those attacks. And then later down the road, we will try to expand it to actually be a production WIDS. So this is Network Recon is the second module that we try to implement. We implemented 3 modules for this release, AES-CTR being the first one. So beacon requests are legitimately used by Zigbee to do discovery. It can also be used as by an attacker to perform network recon, and you can leak a lot of information with a beacon request. So we implemented a module. So first of all, this is how easy it is to send beacon requests with Killer Bee. We also have Zigbee Stumbler, which is just a package tool that will do it for you. So let's take a quick look at what the analytic module looks like. So we have a base analytic module class that we extend, and one of the first things that you do in this highlight with the yellow box is...
It was claimed it was there.
Oh, that's fine. So here where it says parameters, that should look somewhat familiar. So when we were tasking the drone earlier, those are the kind of things that we used. So where it says UUID task 1, we're tasking the drone, and then down here we start, move to the next slide so we scroll up. After we define some very simple statistics, and then we start pouring the database for those beacon request packets. And really all we're doing is some very simple statistics to establish a baseline, and if that baseline threshold is extended, then there's potentially someone doing some kind of network reconnaissance. And if that condition is met, then we register an event to create an alert. And I think we show that on the next page. Using Zigbee Stumbler, when you launch it, just like we saw in the previous demo, magic will happen and we'll get the WIDS alert. And the third module that we implemented was to detect disassociation frames. So legitimately in Zigbee, these are used to ask a device to leave a network, and by an attacker it can be used to DOS it, or as a prelude to more complicated attacks. So again, something that's very simple to detect. Let's take a quick peek at the module. Oh, this is how we implemented it. So we wrote an attack script, and you pass it these parameters, and on channel 15, it'll launch a flood of 5 disassociation frames. So that's kind of what we're looking for. So I don't think we show it here, but we did, as in the previous module, we set up our parameters, we tasked the drone, and we said, hey, we want you to look for these particular frames, in this example for disassociation frames. And then we start to query the database, and then we do some additional logical checking. So if it's a disassociation frame, and if it meets these specific parameters, then an alert is generated. And on the next page, I think we show that. We launch the attack script, and then we get magic. We get a detection. So right now, the framework is very much a proof of concept. It's very simple. It's intended at this point to be sort of a research tool to see how we can potentially detect attacks. Right now, it's limited just to capturing packets and bringing them back, but eventually we can write custom plugins to do some front-end detection for maybe jamming or some other type of attack. So the goal is to provide this tool for the community to be able to extend it via plugins and modules and see what we can come up with. So now we're going to pass it off to Ryan to talk about some Evasion stuff.
This is the first, I think, Zigbee talk I've given that we've had a defensive component in it. I'm very happy that we had a defensive component in it, but I was also told that we should have an evasion if we present a WIDS module. So here we go. Here's how can we evade the system we just made. Is that cheating or not? Going back to what Sergey talked about earlier, this is a different view of the phi layer, right? And what you see is the whole string of nibbles would be that bottom, the PPDU, as the spec would say. And then you have that, that's broken down in your synchronization, your preamble, your starter frame, your packets, and then your MAC layer on top of there, and so forth. And as Sergey said, that's really just bits coming across the air, coming across your bus into your radio jet. So, packet and packet.
Packet and packet. So, actually, let's go one slide earlier. I'm a radio chip. What's my life? What do I do? I pick bytes out of the air. I examine them, each and every one of them. I look for the starter frame delimiter. If I actually do see a starter frame delimiter, I get into my packet mode. I'm in frame. So light bulb goes off. And from that point on, the bytes that I take out of the air, I give to the microcontroller. I accumulate them in a packet and send the whole packet if I have one of the flags in my register set. Or I just give it byte after byte after byte as I am in the packet mode and I have matched the starting frame delimiter. This is all that this radio does. The same way as it receives, it transmits. It receives a packet, accumulates it in some register over the serial bus, then pushes out that buffer byte by byte by byte. And so you sort of ask yourself, I mean, where am I being lied to? How is a sausage made? I mean, what are frames made of? Okay, there is preamble, and then there is the sync. What happens if the can we do shadow pointing?
I don't know.
Yeah, I could.
Yeah.
What happens? What happens if the sync occurs in the body of the packet? Well, now it's not a sync that controls my behavior. It's just an innocent bit of data that I pass, byte of data, that I pass to my microcontroller and up the stack. Now, what if it's followed in the body of the packet by the preamble and preceded by the preamble and followed by a body of a packet with a valid length and checksum at the end? Okay, so this is radio. There is noise. What happens if the true sync, right up there? What happens if the true sync, there, oh, this is, you know, the reach of the hand. Don't you just love weapons? So what if the true sync is stepped on by noise? And radio noise, by the way, is not just white noise. It comes in spikes. It can kill off one nibble, or it can kill off, that is to say, change that nibble to something else. Remember, as a chip, I keep pulling bytes out of the air, even if there are none. I don't know if it's a faint whisper or noise. I don't. So what happens if this sync is stepped on? Well, then this and this and this and this and this and that are just noise, right? I'm not in the packet mode. And now I see a preamble. I synchronize, and look, there is a sync. Hey, now that must be a frame. So I am pulling this frame in. I'm checking its control sum, and yeah, it fits. So instead of the frame that I actually was supposed to transmit, the frame that actually was transmitted, I get something else. Now, which layer is this? This is layer 4. This is application layer. If you control the application layer in a noisy environment where this scheme, preamble, and SFD is used, if you control the application layer, you can inject into the PHY layer whatever the hell you like without owning a radio, using somebody else's radio. So this is packet and packet. And we presented that in 2011. But that actually tells you about how this radio actually works. So there's nothing magical about the preamble and SFD. You can have them in exactly the same modulation scheme in the body of the packet and actually cheat the radio into receiving what was not sent, what was not meant to be sent as such. It gets better. If you look at Travis's article in the journal, you would see that, in fact, you can hear a frame. You can receive a valid frame that was never sent. All the bytes on the transmitter were different. But in fact, you will be seeing a frame that you did not expect. So, stop. what is our game plan? We are going to transmit frames that some radios receive and others do not. This is not about signal strength. This is not about range. This is not about one node being, this is not about the hidden node, one node being too far from a receiver to be, one receiver to be heard, and but close enough for another one. No, this is going to be about the 5-frame formatting. We're going to modify the sync. Luckily, the radio chip allows us to do so. And so we are telling it, oh look, the sync is something else, not A7. So what other receivers will be hearing when we transmit this is nothing, just this nibble that is inconsequential, that would not cause them to go into packet mode. And then in the payload, we can transmit any sequence of symbols that we like. One thing that we can do is we can even do packet out of packet. We can send a packet. We can claim that we're sending a packet, send a short packet, send a higher length, though, and see what the receiver hears after we stop transmitting. Think about that. You will not always get a valid frame. The checksum must match. The checksum is 2 bytes. That's often enough. So then we want to know what frames some radios will receive while others would not. What if we shorten the preamble? What if we send the start of frame delimiter with one erroneous bit? Will it match? What if we send garbage between the preamble and the start of frame delimiter? Would they, in fact, the preamble is not matched as such on most radios. It is used to synchronize the clock. So we built this a system called Isotope. And the name came out of an argument between Travis and myself when we first met. And I was like, hey, fingerprinting. Let's find out how these things differ and how the different receivers receive things. And that will give us something really interesting. And he's like, fingerprinting? Who wants to do that? I mean, where's the ponage in that? This sounds like an academic paper with tables and graphs and no sense whatsoever. Yeah, well, work has been done, money has been spent. Yeah, paper has been covered with
and it has tables and graphs.
And it has tables and graphs. Eventually the packet-in-packet came out of it. The ability to control somebody else's network, if you radio network, if you just control its application layer. And yeah, this is ponage enough. That got the pony at the Black Hat Awards. And now this brings us the WIDS Evasion. So why Isotope? Because chemical elements, I mean kernels of a particular chemical element, are not quite like each other. And you may be really, really wondering why and what sort of boring geeks study that and what might proceed out of that. And then, of course, you discover uranium. And there is one with a tag of 238, 235. And then there is a one of 238. And then it goes boom. So this
does not go boom.
Yeah, so this is a WIDS Evasion.
Okay. So I'm going to go through one type out of the Isotope framework, and there's different techniques we've tried and different tables and graphs that have come out of those, and they aren't any more interesting to me than they probably would be to you, so we're going to try to keep them to a minimum. But Franconian Notch is one we chose because, as I said, we needed a WIDS Evasion for the talk. And so we looked at two radios, the Atmel RZ USB stick, which is uses an Atmel RF chip on it, and then the Apimote, which uses the ChipCon 2420. And we said, what in our tables and graphs does one here, does one process as a valid radio frame, but the other does not? Now, these are both IEEE compliant 802.15.4 compliant 5 chips. We haven't, on the receiver of the app emote, we haven't reprogrammed it. We haven't cheated, I promise, and you can check later in our code. But they actually, some receive and some don't. So Franconian notch is the idea that you take that preamble and you try it with all zeros like it's supposed to be, or you add 2 Fs at the end, just because we picked Fs. Or you try it with 4 Fs, or you try it with 6, or you try it 8. And now, I mean, if you have 8 Fs, right, you have no synchronization happening here, right? So this should not work. And it generally doesn't. But what you find interesting is that there are these times where some, and I have the names of the sticks, but what's important here is to really think of the PHYs, so the ChipCon2420, and the Atmel RF chip that you will have to find me when I can look at my laptop and remember the name. And you will see here that surprisingly, the RZ USB stick, the Atmel compliant chip, will receive frames, you know, pretty well with 2 to 4 nibbles of Fs at the end of the preamble. Maybe its synchronization is more efficient. I don't know. I can't explain, and I certainly can't explain why these test results, which we've rerun so many times, seem to think that it's better at receiving invalid preambles than valid preambles. We've reproduced it in different RF environments. We've rerun this test 6 days in a row. I will continue to work to figure that out, and in the meantime, I don't know. But what's important here is to look at the overlap of the tables, right? This that's supposed to be highlighted but is not, right? This row, the 991 versus 0, the 990 versus 0, right? So when are we looking at 99% reception on some and 0% on the other? So, to show you that we can do this for WIDS evasion, I start up Wireshark, right? I start 2 Wiresharks on the same computer with 2 radio interfaces sitting next to each other on my table. And on another computer, I start injecting. Using the packet and packet, like Sergey said, to control the low layer PHY, we try with 4 preamble bytes. We try with 3 zeros and then an FF. And we go on and so forth. And this is the capture taken from the RZ USB stick. And I've overlaid what preamble, because Wireshark, of course, does not show you that, right? That's part of the nibbles on the air, that's not part of the frame. I've overlaid, based on the sequence numbers, which we altered to make this traceable, which ones were there, and let me show you the app emote. You can verify that the epoch time, and I didn't cheat on this, on the computer is the same. And so now you see that some packets, right, I only see sequence number 1, 6, 11 here, and so 3 and 4 are being received as valid frames by the RZ USB stick, but not by the ChipCon2420 on the app emote. And that's the evasion to the WIDS we just made, so we'll have to work on how to fix that. As you see, those are the frames that match up. The others in between them were not seen by one radio, but were seen by another. That brings us to a point where I really want to open it up for questions. One app emote for the best question, and one for the one that stumps me and makes me say that I will follow up with you later. What would it be if we didn't encourage that? As we mentioned, we've open source released both the WIDS and the app emote hardware as open source hardware today as a Troopers release. And that you can find the links to on our page. Kilobee WIDS, please search and replace with, what are we calling it?
Beekeeper.
Beekeeper WIDS, thank you. Any questions for any of us?
And we will be auctioning. Well, we will donate a number of those to troopers, and they will be auctioning it
As part of the charity.
As a part of the charity auction. And if you need one for your project, just ask.
One question there.
Where was the question?
Yeah, here.
Okay, could it be for the funny thing of the symbols on your Franconian notch? Later, I would really love to hear what its name is. Anyway, could it be that actually there's RF noise that is happening on the preamble, that actually some of the FF symbols are replaced at the radio reception by the receiving stick as zeros, explaining why you have a statistical degradation on your progression on this notch?
No, I think you're definitely right. And if we use things other than Fs to replace those, we could see a totally different spread of how radios receive these. Because the symbols generated from the encoding scheme that the radio chip uses, when those Fs are put on, right, that gets translated into a sequence of bits, and those interplay with noise, like you say, is right. I will let Sergey answer the Franconian notch.
Yeah, so, yeah, sort of slipped. We've been trading those names around the lab for quite a while, and eventually just forget that you need to explain the sort of the lab joke. So, joke explained. Cumberland Gap is a feature of Travis's native Tennessee geography. It is, in fact, a famous mountain gap through which colonists entered and spread further. So there is a song which I'm not going to sing because everything that I sing magically comes out as "Hop on the Magic School Bus," which I'm not going to sing either.
But Franconian Notch is a mountain pass in New Hampshire.
So the first method was called Cumberland Gap, and it filled the preamble with actual garbage. Franconian Notch is another mountain that's nearby, so we came up with that method. So we had to choose a New Hampshire mountain as opposed to a Tennessee mountain, and there it went. There are some more, and you're welcome to the technical report.
Other questions?
Maybe it's a stupid question, but to me this Apple chip looks like the behavior of the Apple chip to the faulty sequences looks like a noise cancellation or like a improvement, like a feature, which means our products are more resilient to radio noise. I'm not sure how to evaluate this. Is it which one would you choose in the production environment? The error forgiving chip or the standard abiding?
The answer to this is yes. Observe, this is a fundamental problem of computation theory, if you will. You have two different automata, right? How do you check the correctness of one with the other? How do you even check that they accept the same language of radio waves or nibbles or characters? This has been pointed out for TCP/IP a while ago. In 1998, Ptacek and Newsham had this genius paper on IDS evasion, which went something like this. If you can make the IDS see a different stream of packets than the target, then you can confuse pattern matching on the IDS chip, by simply throwing in some extra characters that throw off the pattern matching. Whereas the target will receive the payload weaponized and unadulterated by any, and this cuts both ways. Your IDS may not hear some packets that the target would hear. And from that point on, it became clear that in order to protect a stack, you need the same stack, which you of course need to protect, which means that you need an intrusion prevention system for your intrusion prevention system. So,
very true. And one thing I would say, we played with a lot more chips than just these two. The one thing of note is the CC2420 has registers that allow you to, that we didn't play with here, right? It had the default preamble length from SMT, but you can change the preamble length required by the sending or receiving on the CC2420 to be a lot more noise resilient by increasing, first of all, changing away from an A in your SFD based on how the encoding's done might help reduce noise. as well as requiring more bits of preamble length. I think you can have up to 16 on the chip by just poking into a register.
But by making your chip less less susceptible to noise, right? More noise resistant, you just open the way for your system to receive packets that others would not hear. You've basically allowed us to lay a shaped charge to these radios and only these radios in that environment. Isn't that interesting?
And in general, I would welcome people who would like to play around with this for the purpose of figuring out why. You know, we've looked at the published state machines, right? There's a certain level that we can't see about what's happening inside these chips based on the dots we have. I would welcome people to play with us on why is this happening, right? And what's happening at the noise layer with an SDR.
And also observe, you know, now that you're free of the fairy tale, the lie that is the frame, well, fairy tales have their uses, but now that you're free of the fairy tale, now that you've chosen, you know, the red pill, you can produce preambles of any kind and see how your radios react to them. You can come up with your own favorite evasion for your own favorite needs just because you can. And this is, you know, what hacking is all about.
We have 2 minutes left, so we'll take one last question. And then anyone will be around outside. We have circuit boards so you can play with. We can.
So have you delivered the?
One last question, Ryan.
Have you paid out?
Okay.
Sir.
Just to delay my own presentation.
Please.
So you gave an example of Wi-Fi at the start, I think, of a system that had a faulty specification, was broken very early. They slapped on a whole bunch of other things on that. What is the room play in Zigbee for doing that?
So there are additional security suites that can be added at the Zigbee layer instead of at the 802.15.4 layer. These are used in applications, luckily, like smart energy, where key distribution is not done in plain text, right? As it is done traditionally in 802.15.4. Or plain text.
Over the air.
Over the air key delivery, right? So there are extensions for security headers, and it gets a little confusing because you actually, in a lot of packets, have 2 security headers and 2 security schemes happening at the same time in production environments, whether on purpose, maybe more crypto automatically is better, says the implementer, or they don't know what's happening, I don't know. But there's sometimes these dual crypto stacks. So I think there is room, to answer your question, for adding extensions. However, what we focused on here was really going within the specification, right? The attack that Javier talked about with the beacon discovery. That is for the specification, and by design in the specification, beacons and beacon requests cannot be encrypted or authenticated by any key, right? It would take a revision of the IEEE 802.15.4. On the other hand, when you get into the higher layer Zigbee network stacks, there would be, I think, the opportunity to add security. But how much it impacts the text that we talked about at the PHY and the MAC layer? I don't think so. And that's actually one of the reasons we've been focusing at that layer. Everything higher has to use it.
And also, if you're concerned about your wired network, perchance, there has been an effort that is called fully arbitrary 802.3 packet injection. That's your Ethernet, maximizing the Ethernet attack surface, by Andrea Berisani and Daniele Bianco in last year's Black Hat. And they built a card that can manipulate the preamble on Ethernet. And by the way, Ethernet, the different variants of Ethernet follow the same scheme of a preamble, start a frame delimiter, length, and so on. So life is going to get interesting not only in wireless.
Okay, Sergey. Thank you very much, Brian. It's a good talk.